Hey everyone, today we're going to dive into a classic chemistry exam problem. But more than just finding the answer, we're going to break it down step by step to really understand the secrets of acids and titrations.
So think about this for a second. How does a chemist actually figure out the story behind an unknown acid? You've got this clear solution in a beaker, but what's its true identity? How strong is it really? And what's going to happen when you start reacting it with something else? Well, that's the mystery we're going to solve together today.
And here's our game plan. First, we're going to figure out the acid's true identity, kind of like finding its unique fingerprint. Then we'll dive into the titration challenge, predicting how it behaves at some really key moments. After that, we'll put it in a conceptual showdown, strong acid versus weak acid. And finally, we'll wrap it all up with the big takeaways you'll want to remember.
Okay, let's get into it. Our first job is to calculate something called the acid dissociation constant, or Ka. Trust me, this little number is everything. It's the key that unlocks the acid's personality, its strength, and how it's going to act in a reaction.
Every good mystery starts with a clue, right? Well, here's ours. We're told we have a 0.100 molar solution of nitrous acid, and someone's already measured the pH for us. It's a very precise 2.1975. Believe it or not, that's all we need to get this whole investigation started. So how do we get from that simple pH reading to the all-important Ka value? Well, we just follow a straightforward four-step process. First, you've got to write out how the acid breaks apart in water. Second, we use that pH to figure out the hydrogen ion concentration. Third, we'll set up what's called an ice table to keep track of our concentrations at the beginning, how they change and where they end up. And finally, we just plug those final numbers into the Ka formula and solve.
And after we run those numbers, we get our answer. The Ka for our nitrous acid is 4.3 times 10 to the minus 4. Now, that's a pretty small number, and that tells us something huge. This is a weak acid. It doesn't break apart completely in water, and knowing this value is going to be absolutely critical for predicting what happens next.
All right, we've got our acid's identity card. Now it's time for the main event, the titration. This is where the action happens. We're going to put our acid to the test by slowly adding a strong base and watching exactly how it reacts under pressure.
So, let's set the scene. We're starting with 100 milliliters of our nitrous acid. Then we're going to start slowly dripping in a 0.200 molar solution of sodium hydroxide, which is a really strong base. Our whole goal here is to predict what the pH will be at three very specific moments during this process. First up, we add just a little bit of the base, only 5 milliliters. We're still really early in the game here. We've only neutralized a tiny fraction of our acid. What we've actually done is create something called a buffer solution, and a buffer's job is to resist big swings in pH. And the pH at this point, it's 2.4. Now, notice it went up from where we started, but only by a little bit. That's that buffer in action, doing its thing and holding the pH relatively steady. Now for what is easily the most important moment in any titration. We've added exactly 50 milliliters of base. If you do the math, you'll see that at this very moment, the number of moles of base we've added is perfectly equal to the number of moles of acid we started with. This is what we call the equivalence point. So here's the logical question, right? If the acid and the base have perfectly canceled each other out, the solution should be totally neutral. The pH should be exactly 7. That makes perfect sense. Or does it?
But here is the classic twist for a weak acid titration. The actual pH is 8.1. It's basic. So what gives? Well, even though we neutralized the acid, in the process we created its partner, its conjugate base. And because that base came from a weak acid, it's actually strong enough to react with water a little bit, producing hydroxide ions and pushing the pH into basic territory.
All right, for our last measurement, we've gone way past the equivalence point. We've added a total of 100 milliliters of base. At this point, all the original nitrous acid is long gone. We're basically just pouring extra strong base into the beaker.
And as you'd probably guess, the pH shoots way up to a very basic 12.7. The original weak acid is now just a distant memory. The pH of this solution is being completely dominated by all that extra sodium hydroxide we've added.
Okay, this brings us to a really great conceptual question, one that really tests if we understand the big picture. We've seen exactly how our weak acid behaved, but what if we did the exact same experiment, step for step, but we started with a strong acid, like nitric acid instead? How would things be different?
And this comparison just lays it all out perfectly.
At the beginning, the strong acid's pH would be lower because, well, it's stronger. It dissociates completely. Then, at the equivalence point, the strong acid titration would hit a perfectly neutral pH of 7 because its conjugate base is basically useless and doesn't affect the water. But here's the really cool part. Once we're in that excess base region, the pH is identical. At that stage, it doesn't matter what acid you started with. The only thing running the show is the leftover strong base.
So after that whole deep dive, what are the big ideas you should really walk away with? Let's quickly recap what we've learned from cracking open this chemistry problem.
First, Ka is an acid's identity card. It tells you everything about its strength. Second, a weak acid titration happens in 3 distinct acts. You've got the buffer zone, the equivalence point, and the excess base region. Third, and you got to remember this rule, the equivalence point when you mix a weak acid and a strong base will always be basic. Fourth, the real difference between a strong and weak acid is most obvious before all that excess base takes over. But maybe the biggest takeaway of all is this. Next time you're staring down a super complex problem, don't get overwhelmed. Just remember to break it down, piece by piece, into its simple, fundamental building blocks.